So the last concept is binding energy. So we recall that there was some energy released, right? There was some energy released when our atoms came together or when our atom was split apart. So there was some energy released. The energy released is the binding energy. So the binding energy is equal to, so the energy released in that reaction, whether we be fusing them or fissioning them, is the binding energy. Now, also the mass here, right? We can also calculate the binding energy. If we know the mass defect, we can work backwards and figure out what our binding energy is. Now, why is it called binding energy? What about it is binding? Well, imagine that you had two magnets. And they snap together, right? And then this process, when you let them go and they snap together, we release, let's say 10 joules, right? We release 10 joules and now they're stuck together. And so we can ask ourselves, well, how much energy would it take to separate these two magnets again? How much energy would that take? Well, intuitively would say, well, you need to inject 10 joules to separate them back out again. So do you see how this, we can call this the binding energy, because it's the energy that we need to put in to undo the binding, right? When they're in this state like this, when they're bound together, we need to inject energy to liberate the pieces. Similarly, if I have my atom like this, that's all fused together, I need to inject in energy, right? I need to inject in some energy to overcome the strong force between them and to rip them all apart again, just like with the magnets. That's why it's called binding energy. What else is interesting is that binding energy, BE, is an indicator of stability. Is an indicator of stability. As in, something that has more binding energy is a more stable atom. Why is that? Well, imagine this. Let's get back to our magnet analogy, right? Let's say that we had this magnet, which release 10 joules. So I need to put in 10 joules to rip it apart again. And this one, which is, let's say, 100 joules. So I need to put in 100 joules to rip apart this second magnet on the right. That's a lot more energy than on the left. And so you bet, 10 joules, maybe just, if I kick it, it breaks open, just accidentally. If I kick this one, nothing's going to happen because it's bound really strongly. Or maybe if there's an earthquake, right? This one would break open because the earthquake might give it 10 joules, but this one wouldn't. Because you need more energy to put in to break it apart again, so it's more stable, it's more resistant to these kind of changes, right? Now, there is a problem with just using binding energy as an indicator of stability. For example, the binding energy of uranium, which is a radioactive and unstable element, is 1,493 mega electron volts, whereas the binding energy of iron, and iron is very stable. I mean, I've never seen radioactive iron before, is only 493. Oh, I completely messed this up. Sorry. The binding energy of uranium is 1809. So if we just look at this, you'd be like, oh, well, definitely uranium is the more stable element because it's got the higher binding energy. Now, obviously that's wrong because we know that uranium is highly unstable. It's very radioactive. And the reason is because, well, uranium simply has more nucleons. So when there's more nucleons, if you imagine, right, uranium has I think 230 something nucleons, right? So if you imagine the more of these that you have, and remember, all of them have an attractive strong force with each other. So the more of these that you have, the more energy that you need to put in, because you have to remove this one, and this one, and this one, and the more of this that you have, because iron has 5 times as many nucleons as, uranium has 5 times as many nucleons as iron, you need to put in 5 times as much, you need to do this 5 times as many times, you're going to put in 5 times as much energy, right? 5 times as much energy. And so that's going to kind of mess around with it. So what we can do instead is we can calculate something called the binding energy per nucleon. The binding energy per nucleon, or BEPN, which is the binding energy divided by the number of nucleons that you have. So the binding energy per nucleon is a good indicator of your stability. So for example, if we were to do this for uranium 235, so let's do this for uranium 235, we'll do it 1809 divided by 235 is 7.15 mega electron volts per nucleon. We could do this also for, we could also do this for iron 56, which is 493, 56, which is going to be 8.8 mega electron volts per nucleon. And so we can see that for our iron, we have a bigger binding energy per nucleon, which makes sense because if you have a bigger binding energy per nucleon, it means it's more stable, that they hold on to each other with more force. It takes 8.8 mega electron volts to remove each nucleon. It only takes 7.15 mega electron volts to remove each nucleon from that of uranium. So that means that iron is more stable because it takes more energy to rip them apart, right? You'll need a bigger disturbance to rip it all apart. And so if we did this if we calculate the binding energy per nucleon for every single atom, we get this lovely graph. And so we can see here that iron is at the very tippity-toppity peak of the binding energy per nucleons, and so iron should be the most stable. Now, in the next video, the last and final video, we're going to go through analyzing this chart and explaining why fission and fusion are going to be releasing energy in terms of binding energy. See you there. We offer physics, chemistry, and math tutoring. For more insightful explanations like this one, head to tutorgum.com.